Today I'm going to run through a few upper high school level to undergraduate level chemistry questions. So to start us off, here's our first question. So it gives us density for aluminum of 2,700 kilograms per meters cubed, and asks us to find how many atoms are in a 2.6 centimeter cubed volume. Okay, so our density is mass over volume, and so we can get a mass from our volume by rearranging. So it's density times volume, which should then be 2,700 kilograms over meters cubed times 2.6 centimeters cubed. But obviously this is in centimeters. We need meters, so we need to multiply by an appropriate factor here. And so 1 meter is 100 centimeters. And that whole thing will need to be cubed to cancel all the centimeters. And then the meters will also cancel. And so if we run this through on our calculator, we will find this is 2,700 kilograms. I guess I got carried away on the cancellation. Times 1.7576 times 10 to the minus 5 meters cubed. And so now this will cancel, which will equal 47.4552 grams. And I'm just holding on to extra decimal places beyond the significant figures just until the end, so we avoid rounding errors. The molar mass. So now we have a mass, and we want to know how many atoms there are. So we can find the number of moles through the molar mass of aluminum, which is 26.981539. And so the number of moles of aluminum is equal to the mass over the molar mass. So that's 47.4552 grams over 26.9815 grams per mole, which comes out to be 1.7588 moles. Okay, so now we have the number of moles of aluminum. So the number of atoms is just going to be, so Avogadro's number is the number of atoms or molecules depending on what we're referring to, but for aluminum it's going to be the number of atoms per mole. So we've got about 6.022 times 10 to the 23 atoms per mole times our number of moles. And so that's going to equal our number of atoms, which in this case comes out to 1.059 times 10 to the 24. Or rounding for significant digits. In the question, we're given 2,700 without a decimal place there, so that means there's only two significant digits, so that would be 1.1 times 10 to the 24 atoms. Okay. So if we check the solution here, we just perform basically all the stuff that we did here. So except it's all in one step. So there's our volume, conversion to meters, the density, conversion to grams, which I dropped, but I did do in my solution properly, but I forgot to mention it here. Right. So this is correct up here, but I forgot to mention that obviously I had to multiply by 1,000 grams per kilogram. So at this step, I had to do that to get to that answer, but that answer is the correct answer still, or is the correct number of grams. I just skipped that step. And then dividing by the molar mass as we did there, and then multiplying by Avogadro's number, and we get 1.1 times 10 to the 24 atoms. So that looks good. So the solution is correct. Okay. How to calculate the electrochemical cell potential with a solved example. Okay, so we can get our E cell from Nernst's equation. In which E cell naught is our standard cell potential. R is our universal, is the same as the universal gas constant. T is temperature. N is the number of moles of electrons that were transferred, which I'll show in the example. And F is Faraday's constant, which is an Avogadro's, it's the charge on 1 mole of electrons. So 1.6022, 1.602 times 10 to the minus 19 coulombs times 6.022 times 10 to the 23 per mole. So this is about 96,485 coulomb per mole. And the units that are sometimes used, or often used, I guess, is joules per volt mole. So that gives us units that work better for our cell potential, which would be in voltage. And then Q is like an equilibrium constant, but it's computed at not the equilibrium. But the form is the same. And I can't remember what Q's called right off the bat. Okay, so E naught cell can be computed in a number of ways. So E naught cell can be computed from a known equilibrium constant. With the same form as this, but so basically what your electrochemical cell potential is the difference between the state at equilibrium and the current state of the system. So that makes sense. I'm going to make make sure that's more of a K so it doesn't look so much like a rate constant. But also you can get it from your Gibbs, your standard Gibbs energy or your standard Gibbs change for the reaction, as this is equal to RT ln K. And so your standard Gibbs is minus NF E naught cell. So you can obtain your E naught cell from your equilibrium constant or from your Gibbs free energy change. But also you can get it from standard electrochemical cell potentials, as I'm going to do in this example here. So another way is to get E naught cell from E naught cathode minus E naught anode. Okay, and so if we had a cell like aluminum, Three plus, and so this is an aluminum copper cell. And so this is kind of a typical drawing for a battery, where this is indicating our reactions that are occurring. And so we have aluminum solid going to aluminum 3 plus 3 electrons. And we have copper 2 plus 2 electrons. Oh, I guess I should have, well, going to copper solid. Right, and so so if we have to balance the number of electrons that are being transferred. So the other way to do this is to multiply this by 2 and multiply this by 3. And so then we'd have, and then we sum the reactions, and so we'd have 2 aluminum solids plus 3 copper 2 plus going to 2 aluminum 3 plus 3 copper solid. And so in total for the reaction then we have 6 electrons being transferred. So I guess I should have kept the electrons instead of canceling them. Right, so we have plus 6 electrons on this side and plus 6 electrons on this side. And so we have 6 electrons. And so that means that our N in our Nernst equation is 6. Okay, and then if we're given 2 standard cell potentials, so E naught cell is minus 1.676 volts for this. What did I do? Three, 4, 1, 9 volts. Okay. Okay, so in this case now, so our cathode, we could either apply it as E naught cell is equal to E naught cathode minus E naught anode, where our anode would be our cell that's producing our electrons. So this would be our anode. This here would be our anode. And this would be our cathode. Often what I do to remember this equation, or to remember how to apply it, is what you really need to do is just have the two match what is in the question, and then just rearrange, because your E naught cell will actually be the opposite side, will change sign. So if we switch this to aluminum solid, goes to aluminum 3 plus 3 electrons, then your E naught cell becomes 1.676 volts, and then your E naught cell in this case is 1.676 volts plus that for copper, because it matches what it's supposed to in the question. Which comes out to be 2.0179 volts. So we can either reverse the direction of the equation and then just sum the E naught cells, or apply this simple equation after recognizing which one's the cathode and the anode. And so this one's the anode, this one's the cathode, and so we could say E naught cell is 0.3419 volts minus, so the E naught cell for the aluminum cell is negative 1.676, so minus a negative 1.676, which comes out to be 2.0179 volts. Okay, so we can apply it either in this form, or I find it easier to just reverse the reaction, whichever reaction is necessary, swapping the sign on the E naught cell when you do it, and then you just sum the two. But it's up to the viewer to figure out which method they find works better for them. Note here that I didn't multiply by any coefficients, so none of so in doing this, the equations don't balance, right? So all the balancing is done actually in the prefactors on our E cell, right? So our E cell is now E naught cell, minus RT over NF ln Q. And so all the balancing is done by having the N there and in the Q. Okay, so now we've got our E naught cell, and we're given in the question, which I'm just going to scroll back up to see again. We're given in the question that we have 0.15 molar of aluminum and 0.025 molar of copper 2 plus. And if we look at our balanced equation, which I'm just going to copy down here. Okay, so just as a reminder here, so we have aluminum, 2 aluminum solid plus 3 copper 2 plus goes to 2 aluminum 3 plus 3 copper solid. And so our Q, where aluminum 3 plus is 0.15 molar, and our copper 2 plus is 0.025 molar. So our Q is just our concentration of our products, where we don't include solids in that, just like in the case of our equilibrium constant. So it'll just be the concentration of aluminum 3 plus squared over the concentration of our copper 2 plus cubed. So in this case, it's 0.15 molar squared, and actually you just cut the units because Q needs to be unitless. Cubed. And so if we work this out, it comes out to be 1440. And now, now we're ready to apply Nernst's equation. And so our E cell is our E naught cell, which we calculated as 2.0179 minus, and so this will be our gas constant in joules per mole Kelvin, so 8.314 joules per mole Kelvin, times our temperature. In this case, we're just going to use 25 degrees Celsius. And we had 6 moles of electrons transferred. So we use 6 and 96,485, and that's in joules per mole volts. So our joules will cancel, our moles will cancel, and our Kelvin will cancel, giving us an answer in volts, which is good because that is in volts. And then times the ln of 1440. And that's the natural logarithm, just to make a note of that, not the base 10 logarithm. So when you use your calculator, it's not log, it's usually second the E, just so you don't make any mistakes there. 2.0179 volts minus, this comes out to be 0.0042819 volts times 7.272, or 2.0179 volts minus 0.03114, which comes out to be about 1.99 volts. And just a note for any other additional questions that would be asked in something like this. So if the E cell comes out to be positive, then that means it's spontaneous in the direction that we're writing it. And so then the electrons, as we draw it, would flow, and we'd have, as we have a positive cell potential. Yeah, okay. So that's That's how you would calculate each cell in most cases, as you'll probably be given these E0 cells, but it's also possible you'd have to use delta G, which I briefly described above. Okay, so just checking the solution here, so that it's probably going to be different than mine. You can use this. You can use the Nernst equation where your E0 cell is computed from your cathode and your anode. So we can get standard potentials. So this just describes each of the constants. Here we have a slightly more complex example with many other constituents. We identify the number of electrons in each of the half reactions and are given standard potentials. And then we just need to, actually in this case, as they're in the correct directions, we would just need to sum them. Okay. So Q is computed from your concentrations, which is what they've done. Should not be, oh, these are reducing potentials, not cell potentials. Okay, that makes sense. So that is the negative of the standard potential. Okay, so then we're going to just have E0 cell, which is this, and plug in all of our values. So the temperature here was 300 Kelvin. There's our gas constant, there's our Faraday's constant, and the number of moles. And so we'd get something like this, and that looks good. Okay, all right, so pi electrons in an aromatic compound. So just a note here, so pi electrons are basically, for all intents and purposes, in double bonds. Not necessarily just in aromatic compounds. So in an example like this, we have 2 sigma electrons and 2 pi electrons. It doesn't matter which of the 2 bonds you call your pi electrons or your sigma. I'm just picking one, but there really is no way to differentiate from a simple drawing like this. Or in the case of, say, like nitrogen, we have 2 sigma electrons and 4 pi electrons, as 4 of the electrons are in pi bonds. So a pi electron just refers to an electron that's in a pi orbital, which for multiple bond cases is everything except one of the bonds. But in an aromatic compound, this can get a little tricky. As I'm going to show with a couple examples. So for aromatic compounds, what we need is for the number of pi electrons to equal this, where n is any integer. So basically, another way to phrase this is to say that n should equal the number of pi electrons minus 2 over 4. and that this should come out to be an integer. So some examples here. So for say C, so for this case, which would be cyclodibutene, we have two sets of pi bonds. And so there are 4 pi electrons. So then n would be 4 minus 2 over 4, which equals 2 over 4, which equals a half. So that's not an integer expression, so this is not aromatic. Now, if we have a case like benzene, trying to draw, okay, there we go. If we have a case like benzene, which everyone knows is our kind of titular aromatic compound, this has 6 pi electrons, right? So n is 6 minus 2 over 4, which equals 4 over 4, which equals 1. So that is an integer, so this is aromatic. Now, more exotic examples include things like the cycloheptane anion. Okay, and so in this case, we have 4 pi electrons here, but then also this lone pair is included. And so the reason for that is because what we're really looking for is a number of pi electron, or a number of p orbital electrons. So one other easy way to remember this is really the number of p orbital electrons. And so that's a little bit more general. And what I mean by that, I should put a negative sign there. What I mean by that is in each of these carbons, they're sp2 hybridized. And so that's where the sigma bonds come from. Whereas the pi bonds come from an electron in a p orbital that sits on the carbon. So if we split everything in this, then it would be something more like this, where each of the carbons here has a single electron, and then this one has 2. So kind of in a Lewis type diagram. This isn't really anything you can do, but this is just to note. So this is really the number of p orbital electrons here is, again, 6. And then this is what forms our pi bond there, and that forms our pi bond there. And then this lone pair gets included in our pi electrons. So then here we have n equals 6 minus 2 over 4, which equals 4 over 4, which equals 1. So this compound is aromatic because there's 6 pi electrons. And so the easy way to remember, like I said, is number of p orbital electrons. So another example of this is in furan. Where again we have something that looks similar to what we had up there. I'm just going to add these hydrogens in quickly. And so it looks like maybe we have 2, 4, 6, 8 pi electrons, but that would also be incorrect. And so one rule of thumb, at least in a cyclical compound like this, is that if we're connected to sp2 hybridized atoms, then this also must be sp2 hybridized. But another way to look at it is to be in a ring structure, this has to be bent. And so this must be sp2 hybridized. Okay? Which means that we need 3 bonds in our sp2 hybridization. So we have these 2. So then one of these lone pairs is in an sp2 orbital, and then the other one is in a p orbital. And then again, we go back to our p orbital count, right? And so if we re-sketch this like this, where we're only showing the p orbitals, then it would be something like this, where now we have 6 p electrons. And so n is 6 minus 2 over 4, which equals 4 over 4, which equals 1. And this compound is aromatic. Okay, so this kind of sketches out another example, which can cause some headache, especially just because of the 2 lone pairs, but only one of them is actually included, as the other one must be in this sp2 hybridized orbital. Okay. And I can do plenty of other examples, but I think that's probably enough for this simple question. And so there's a few examples here showing that the diheptene is not, benzene is aromatic, and then the cyclooctene is also not. So that, I think, looks pretty good. It doesn't cover some of these extra examples, but that's fine. Okay. Okay, so for this, actually, I'm going to go to here. Okay, so what is the electron configuration of scandium? So for this, we just need to locate scandium on our periodic table, which is here. And to get electron configurations, we just run across, and remember helium should be about here. So for scandium, we have 1s2, and remember this is the s block, p block, d block, f block, and the f block gets inserted here. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d1. Okay, and so that's the order in which everything's filled. Now, just to take a bit of a note from the way the solution is posted here, we can always write our configuration just to save space in terms of our highest noble gas. So in this case, it's argon. So my argon is mislabeled, but it's argon. And so we can call this our argon configuration. And then, although the way I ran through it shows the proper way to fill, the 4s2 is still the outer shell. And so it'd be 3d1, 4s2. So we would swap, we would write it from lower principal number to higher principal number. Which also would just make it easier for doing ions. And so if we look at the solution here, that looks good. So it's correct. And so now my next question here is to do zinc. Specifically Zinc 2 Plus. So I'm just going to erase some of this. Okay. So first we just need to find zinc. So it's here. And now we just run it across. So to get Zinc 2 Plus, we need to start off by finding what the configuration for zinc is. And so it'd be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Now, to get Zinc 2 Plus, we remove 2 of the outer shell electrons, so those would be electrons with the highest N. So that would be these. So then our configuration would be 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. Okay, so we always we fill up basically following the periodic table, but in making an ion, we remove electrons from our highest N orbitals first. Okay, so and it forms our 2 plus cation. It loses 2 in the outer shell, causing the 4s to be removed, and so we get that configuration, which looks good. So our solution is correct. Okay, so what is the molecular geometry of pH 3? Okay, and so in all cases here, so our valence electrons on phosphorus are 5 valence. Hydrogen each has 1, so we have 8 valence electrons. Start off by just attempting to do a simple sketch by putting our constituent atoms around with their appropriate valence, and then drawing a line, and that looks good. So our octet is satisfied for phosphorus, and there's 5 electrons here, so it's neutral, and so this looks good. If we were to draw the structure, it would be something like this, where I'm using filled in wedges to show it's coming out of the page and the hash to go into the page. And so our electron geometry is AX4 or tetrahedral. And our molecular geometry is B for a lone pair, AX3, which is trigonal pyramidal. Okay, so our molecular geometry is trigonal pyramidal. Okay, so we get our simple Lewis structure. We have one lone pair and 3 bonded pairs. This person used an E for the lone pairs. You can use whatever you want. I just used B because that was the first thing that came to mind. And so you determine your molecular geometry. A lot of times there's either tables for this, or you can memorize it. Eventually you probably will as you go through this enough times. And so the molecular geometry is trigonal pyramidal, which looks good. So the solution is correct. Okay, so for this one, which is, I guess, my 7th question, it's why is CH3OH an Arrhenius base? So in the Arrhenius definition, which is kind of our most primitive and is almost never used, OH minus is the only base, or OH, any substance that can give you OH minus is a base. And so this is not an Arrhenius base. Because it can't dissociate to give you OH minus. In fact, CH3OH can donate a proton to give you CH3O minus plus H3O plus, and therefore it's actually a Lewis acid, or not a Lewis acid, sorry, a Bronsted acid. Okay, so an Arrhenius base needs to be able to yield OH minus. So it's not an Arrhenius base, but it is a Bronsted-Lowry acid. So this looks correct in that they've correctly said that methanol is not an Arrhenius base. Okay, draw the Lewis structure for the fulminate ion. So we have C and O minus. So in this case we have 4 valence here, 5 valence here, 6 valence here, and we need to add 1 more. And so our total is 16 valence electrons. As always, I will try to just place them in and hope that this is going to work. All right, and bond them up, and already we have an issue. We still need to add one more electron for the negative, so we might as well put it on the oxygen. And so the oxygen has a full octet. There's 7 electrons, giving us a negative. But then these two don't have a full octet. We can double bond here. But there won't be a way to fill up the octet without moving this electron over here and then giving us our triple bond here. And so we might as well do that. And now nitrogen has, now everyone's octets filled, which is good. Nitrogen has 4 around it, making it positively charged. Carbon has 5 around it, making it negatively charged. So, but that's the only way for us to get our octet satisfied. And so this is the most likely structure, as -1 + 1 -1 is still minus. And so this looks to be our fulminate ion charge, or our fulminate ion structure. Where the charge has been distributed across carbon, nitrogen, all 3 atoms, but we have a bit of separation from the center. Okay, so this is the Lewis structure that was come up with. That looks good. C and N don't have a formal charge of 0. In fact, carbon's negative and nitrogen's positive, but O is negative. The total charge is that though, but as far as the structure, I'd say it's correct. I'll say structure is correct. Structure is correct. Note that the charge on C is -1 and is +1. Not 0 as stated in the solution. But the question is just to draw the Lewis structure, so I'd say it's correct. It's just a bit, some of the answer is a bit misleading. Okay. Is the compound NH2 minus polar or nonpolar? So to answer this, we need to draw it. So for NH2 minus, we have 5 valence on nitrogen, 1 on hydrogen. So there's 2 of them, so that would be 2. And then we have to add 1 more for the negative. So our total is 5, 6, 7, 8. So 8 valence. And so we'd have N. And just going to start off by, again, placing things in. We have 1 extra valence electron, though, that's not depicted here, so I'm just going to add it in around the nitrogen, and then do our bonds. Okay, so that looks good. When we draw the 3D structure, our electron geometry should be tetrahedral. So that would be a lone pair above, a lone pair over here, and then the hydrogens would be out of the page and into the page. So our electron geometry is AX4 or tetrahedral. And our molecular is bent, or B2AX2, where I've used B for the lone pairs. And the negative sign sits on the nitrogen, as there's 6 electrons around nitrogen. And so now we're going to have a dipole here, a dipole here, and so this molecule, since it's bent, is definitely polar. So because it's not perfectly symmetric, well, it's symmetric, but because it's the dipoles don't cancel from the bonds, it's polar. When we talk about polarity, we talk about covalent ions. Since ions, the charges are far more significant, NH2 is neither polar nor nonpolar. So NH2 minus is polar. I don't know necessarily what they're talking about there, so I'm just gonna say it's incorrect. Okay, now what is the pH of a 0.15 molar solution of sodium acetate? And it gives us the Ka for acetic acid. Okay, so sodium acetate, we are going to assume completely dissociates into Na plus C2H3O2 minus, or our acetate ion. And then in solution, our C2H3O2 minus is going to react with water to give us acetic acid and OH minus. So it acts as a base. So acetic acid is our conjugate acid. And so we can use this expression to obtain our Kb. Ka, Kb is Kw. So this relates the K constant for a conjugate acid-base pair to the Kw constant, where Kw is 1 times 10 to the minus 14. So our Kb is Kw over Ka, which is 1 times 10 to the minus 14. And using the value given in the question, 1.8 times 10 to the minus 5, which comes out to be 5.56 times 10 to the minus 10. Okay, so now we're ready to, so now we have our Kb. We can start to solve the question. So here's our balanced chemical equation. And so we need to figure out our concentrations of our constituents at equilibrium. We're given that we have a 0.15 molar solution of sodium acetate. We assume that completely dissociates to give us 0.15 molar of our acetate ion. So that's our initial. And then we have 0 of those initially. Our change is going to be minus x plus x plus x. This is because everything's in a 1-to-1 ratio. And then our equilibrium is going to be 0.15 minus x, x, and x. And so our Kb in this case is going to be our products over our reactants. So concentration of acetic acid, concentration of OH minus, over the concentration of our acetate ion, which is just x over 0.15 minus x. Now, taking our Kb constant, we can solve for x. So 5.56 times 10 to the minus 10 is equal to x squared over 0.15 minus x. To simplify things, we're going to assume that x is much less than 0.15. So this is approximately 0.15. Meaning that our 5.56 times 10 to the minus 10 is approximately x squared over 0.15, or x squared is approximately 8.33 times 10 to the minus 11, or x equals 9.129 times 10 to the minus 6. So that validates that assumption, because 0.15 times 10 to the minus 6 is pretty much 0.15. Now looking at our ice table, our X is our concentration of OH minus. We can get our concentration of H3O plus, which we would need for our pH, by considering our Kw equation. So Kw is the concentration of OH minus times the concentration of H3O plus, or the concentration of H3O plus is Kw over that of OH minus, which is 1 times 10 to the minus 14 over 9.129 times 10 to the minus 6, which comes out to be 1.095 times 10 to the minus 9 molar. And so our pH is just the negative logarithm of this quantity, which comes out to be 8.96. Okay, so now running through the solution here, we get our acetate ion. Acetate is now in equilibrium with our acetic acid. Our Ka and Kb for our pair is related to the water constant, which is 10 to the minus 14. So we can solve for Kb. Use that in our ice table with acetate ion. And then make the simplifying assumption to get our X value. Or actually, they didn't use the simplifying assumption, but you can see that it's only different by the third decimal place. And then, so what they did is solve for POH, and then your pH and POH are related by, they should add up to 14. Or you can use the method I use to solve for your H3O plus. As you can see, it doesn't make a difference as the pH comes out to be 8.96 in either case. So the solution is correct. And I'm actually going to stop it there and say that's all the questions I'm doing for today. Thank you for listening and watching. If you enjoyed this, please subscribe to OneClass. If you want to add questions, please follow the links below the video. This has been Jeff Krause for OneClass, and I hope to